Hi everyone, welcome to this comprehensive guide on high performance liquid chromatography, or commonly known as HPLC. HPLC is one of the most powerful analytical techniques in modern chemistry used to separate, identify, and quantify individual components in complex mixtures. Let's get to know HPLC deeper. So, before we start, let's get to know what is the objective of this experiment. So, first of all, it is to determine the retention time of a standard solution, which is caffeine, and next, it is to identify the caffeine peak in a soft drink sample. And lastly, it is to determine the amount of caffeine in soft drink sample using the response factor method. So, what is exactly HPLC? Let's analyze the name first. High performance can tell us that this particular chromatographic technique has high resolution power. Second of all, liquid act as a mobile phase. So, HPLC is just a chromatographic technique which has a very high resolution where the mobile phases, liquid, pass through a column which act as stationary phase under a very high pressure. A key component of HPLC systems is the detector, which captures and interprets data from separated compounds. There are several types of detectors, each suited for different analytical purposes. Firstly, we have UV-based detectors, which are ideal for compounds that absorb ultraviolet or visible light. Secondly, refractive index detectors (RID). It's perfect for non-UV absorbing compounds like sugars and alcohols. Next, diode array detectors (DAD) are versatile for capturing spectral data across multiple wavelengths. Lastly, mass spectrometry (MS) provides structural information for high precision analysis. In this presentation, we will focus specifically on RID and DAD detectors, highlighting their working principles, advantages, and applications. Now we're moving to the workflow of an HPLC analysis. Firstly, mobile phase selection. A liquid solvent is chosen based on the analytes and desired separation. This mobile phase flows through the system continuously. Secondly, sample injection. The sample is introduced into the mobile phase, usually through an automated injector or manually using syringe. Thirdly, separation in the column. As the sample travels through the column, each component interact with the stationary phase differently, resulting in separation based on the properties such as polarity, molecular size, or charge. Fourthly, detection. The separated compounds exit the column and pass through the detector, which measure their concentrations and provide data for analysis. Lastly, data analysis. The detector output is processed into chromatograms, showing peaks corresponding to each compound in the sample. Generally, HPLC is used in various fields. Firstly, pharmaceutical industry, used for quality control, drug formulation analysis, and determination of active pharmaceutical ingredients such as APIs and impurities. Next, food and beverages industry, essential for analyzing sugars, vitamins, preservative, and other additives to ensure the product quality and compliance. Next, environmental monitoring, detects pollutants, pesticides, and contaminants in water, soil, and air samples. Next, chemical research assists in the separation, identification, and structural analysis of complex chemical mixtures. And lastly, clinical and biomedical application, used for monitoring biomarkers, hormones, and metabolic compounds in biological samples. The RID operates on a simple principles, which is when light passes through a sample, its speed changes based on the refractive index of the substance. RID measures this change in speed, indicating the difference in the refractive index between the sample and the mobile phase. There are a few advantages for RID. Firstly, RID is ideal for detecting compounds that do not absorb UV light, such as sugars, alcohols, and organic acid. It is non-destructive method, preserving the sample for further analysis. RID is cost-effective and easy to operate. For the limitation, it has lower sensitivity compared to UV detectors. It requires stable temperature and flow rate conditions. Lastly, it cannot detect UV absorbing compounds or provide spectral data. Thus, RID is extensively used in the industries such as food and beverage analysis, where it is employed to measure sugar content in products like juices and honey. For DAD, it measures the absorption of light by compounds across a range of wavelengths. As the sample elutes from the column, the detector splits light into its component wavelengths and measures how much light each compound absorbs. For its advantages, DAD provides spectral data for compound identification, making it highly versatile. Next, it allows simultaneous detection across multiple wavelengths. Lastly, detectors offers high sensitivity for UV and visible light absorbing compounds. For the limitation, it cannot detect non-UV absorbing compound. Next, it is more expensive than RID. Thus, DAD is widely used in pharmaceutical for identifying and quantifying drug compounds, in environmental monitoring for detecting pollutants, and in chemical research for structural analysis and impurity profiling. So, the table below shows the differences between refractive index detectors and diode array detectors.
Welcome to the demonstration of our high-performance liquid chromatography HPLC process. In this video, we will guide you through the steps involved in analyzing samples with precision and efficiency. As you can see in this video, we are using a refractive index detector RID as part of our HPLC setup. The mobile phase for this analysis consists of acetonitrile and deionized water. So, this is the pump which is responsible for drawing the solvents and sample into the system. Once the sample and solvents are drawn in, they pass through the carbohydrate column. This column plays a crucial role in separating the compounds of interest. After passing through the column, the compounds are detected by the RID and then collected in the waste bottle. So, our system uses a manual injector. Next, open the HPLC RID software. Before analyzing the sample, check the software interface. All compartments in the system must show green indicators. This confirms that the system is ready for operation. When switching on the electrical current, wait until all the indicators turn green before proceeding. Before injecting the sample, it is essential to ensure that all solvent and samples are filtered using a filter membrane. This step prevents impurities from interfering with the analysis. For HPLC analysis, only a small volume of the sample is required. Prepare 20 microliters of the filtered sample for injection.
Before injecting the sample, click Method and click Edit Entire Method and a page will pop up, so just click Method Information, Instrument, Data Analysis and Runtime Checklist and then click OK. As for method command, just put sucrose 5% and click OK. For injection source, choose manual injector and then click OK, and the software will prepare method editors. A page will pop up and show a quad pump page. The sample must be filled in the correct box to ensure the system to give a nice peak. In this experiment, acetonitrile is in label A and water is in label C. For the flow rate, it need to be adjusted according to the sample. For this experiment, our flow rate is 0.5 microliter per minute and it will affect the pressure later. As for stop time is the time taken for the sample to be analyzed. The retention time for our sample is 15 minutes. After filling in the boxes, click Apply and then click OK. Another page will pop up. For this page, nothing need to be done, just ignore it and click OK. Another page will pop up and do the same thing. Just click OK. After that, another page will pop up and some changes need to be done here. On the report style box, choose Short and click on what boxes that are needed in the report. So here we need chromatogram output and the fraction table and then click OK. Instrument curves HPLC RID page will pop up showing that the boxes that are checked. That is what will appear in the report data, so just click OK. The runtime checklist page will pop up and do the same thing. Just click OK since there is nothing to change. After that, go to File, click Save As Method. If everything has been confirmed and there's no changes on the parameter, input the file name as sucrose 5% and click OK. After the method has been saved, we just need to wait for the pump, column, and the detector to be ready and then can proceed to inject the sample. As for the quad pump, the solvent box can be filled in by clicking bottle filling and fill in according to the sample volume to alert the system. Here, the amount that we use is 0.6 liter and then just click OK. Moving on to column, click Method and the temperature can be adjusted according to the sample. For sucrose, the temperature range is around 25 to 40 degrees Celsius. So here we put 35 degrees Celsius and after that click Apply and click OK. For the detector, there's no changes need to be done as long as the detector is ready, then just proceed to inject the sample.
Now, let's dive into the injection step of HPLC and explore how it works.
In this sample injection step, a very small amount of sample is sufficient enough for this technique. So, sample is injected into the system via a specialized sample injector, which connected with the auto sampler, which can load multiple different samples in a semi-automated fashion in this machine. As for this demonstration, we are using a manual injector syringe. First, take the sample which is 5% of caffeine and inject around 10 microliter. Make sure there are no air bubbles in the syringe. Before injecting the sample into the injector piece, make sure the lever has the correct place in load in order to receive the sample. If the lever is in the wrong position, it will not allow your sample to be taken up into the instrument. At this position, the sample is introduced into an external sample loop while the mobile phase flows directly to the column by passing the loop, then loading the sample and inject. Pull it out, then switch the inject position. For caffeine, the retention time is around 4 to 5 minutes, so we have to put the analyzing time around 10 minutes. The system of HPLC will automatically analyze the sample. The valve redirects the mobile phase through the sample loop, sweeping the sample into the column for analysis. As the HPLC is running, the graph go up and down. At peak indicate the compound or analyte that is exiting or loading. This would be the time to collect a fraction if we are trying to collect smaller piece of sample.
This is the standard caffeine chromatogram, which establishes the retention time and peak intensity for pure caffeine. It shows a single sharp peak at the specific retention time, which is at minute 2.482. The intensity of this peak reflects the concentration of caffeine in the standard. This sample chromatogram shows the presence of caffeine at the same time retention time as the standard. Additional peaks may indicate other compounds or impurities in the sample. The area under the caffeine peak is measured to calculate the concentration using the standard curve. Lastly, this is the result of amount of caffeine in Levita. The calibration curve correlates caffeine concentration with peak area, allowing us to determine the caffeine content in the sample using equation of the line.
Right, now we are going to discuss the calculation of the concentration of caffeine, ppm, in the unknown sample. First, using the formula of response factor, RF, in caffeine standard, we divide the peak area caffeine standard with concentration of caffeine standard. From the result, peak area caffeine standard, which is 6,249.48779, and concentration of caffeine standard used is 5%. Now, we need to convert 5% to parts per million ppm. 5% mean 5 gram of caffeine in 100 ml of solution. So, 5 times 10 to the power of 4 equals to 50,000 ppm. Next, we proceed to calculate the RF. So, 6,249.48779 divide with 50,000 ppm and we'll get 0.125. Next is the concentration of caffeine in the unknown solution. We divide the peak area caffeine in sample with RF, which is 6,249.48779 with 0.125, and this will give us 49,955.90 ppm. To convert this, divide it with 10 to the power of 4 and give the result of approximately 5%.
As for conclusion, the study successfully determined the retention time of the caffeine standard, which was measured as 2.482 minutes. This value was used to identify the caffeine peaks in the tested soft drink samples. The retention times for caffeine in Coke was 2.481 minutes and Lavita is 2.479 minutes, closely matched the standard, confirming their identification. Using the response factor method, the concentration of caffeine in Coke was calculated as approximately 49,995.90 ppm. The results align with the objectives of the study by demonstrating the capability of high-performance liquid chromatography (HPLC) to accurately determine retention times, identify compounds, and quantify caffeine in soft drinks. To enhance the experiment, other instruments like gas chromatography, mass spectrometry, GCMS could be employed for further confirmation of compound identity and to analyze volatile compounds. Additionally, incorporating ultraviolet visible UVVs spectroscopy could provide complementary data for caffeine and quantification.